This is Chapter 11, Section 5, where we're going to talk about the dissociation of water itself. We typically think of water as a covalent molecular compound. However, to a small extent, water can actually dissociate into protons, or H plus ions, and hydroxide, or OH minus ions. From the Bronsted-Lowry perspective, this is more typically seen as one water molecule transferring a proton to another water molecule. In this case, one water molecule is conjugate to the hydroxide ion that results, and the other water molecule is conjugate to the hydronium ion that results. In this section, we're going to learn how to write the equilibrium constant, the dissociation expression for this reaction, and that's going to allow us to calculate concentrations of hydronium and hydroxide ions. Remember that this transfer of a proton from one water molecule to another is reversible, and therefore this is an equilibrium reaction. One water molecule can give a proton to another, and then it can also take a proton back. As with any equilibrium reaction, we can write an equilibrium constant expression. For general equilibrium expressions, this is called Kc. For acids, it's called Ka, and now that we're dealing specifically with water, it's called Kw, the water dissociation constant. It's also sometimes called the ion product constant or the autoionization constant, or a few other terms which reflect the same idea. The expression here is to take the product concentrations, H3O plus and OH minus, and divide them by the reactant concentrations, which are both water. However, since they're both water in the liquid phase, we can leave them out of the equilibrium expression. And so all we need to write for Kw is that it's the concentration of hydronium, H3O plus, multiplied by the concentration of hydroxide, OH minus. Remember that this is a value we can measure experimentally. We take a system of pure water and we just measure the ions of hydronium and hydroxide. At 25 degrees Celsius, what we find is that the value of Kw is 1 times 10 to the minus 14. Clearly, this is a very small number, which reflects the fact that water does not really dissociate much at all. The vast majority of water molecules stay as neutral, intact, covalent molecules, and only a very, very, very small number will actually dissociate into these ions. From this reaction, we can also see that in pure water, every time one water molecule loses a proton to become hydroxide, another water molecule has to gain a proton to become hydronium. What that means is that if the water is pure and there's no other substances around, the concentration of hydronium is going to be exactly equal to the concentration of hydroxide. Since we know that the Kw value is 1 times 10 to the minus 14, and we know that both of these concentrations are equal, we can substitute in the value of hydronium concentration for hydroxide, and then we get that the Kw equals the hydronium concentration squared. Or in other words, in pure water, the hydronium concentration equals the square root of Kw, which is actually 1 times 10 to the minus 7. We could also do it the other way, where we substitute in the hydroxide concentration for hydronium, and then take Kw as the square of the hydroxide concentration, and take the square root of Kw, and we would find the same thing. H3O plus equals OH minus, and both of these concentrations are 1 times 10 to the minus 7. The concentrations that we just calculated for hydronium and hydroxide were really just for pure water. Again, remember that they were equal because in pure water you can't create a hydroxide ion without also creating a hydronium ion. The general value of Kw, however, is true for any solution whatsoever, even if it's not pure water. That means that for any water solution, Kw will always equal the product of the two ion concentrations. And therefore, if we know the concentration of one ion, we can solve this equation to calculate the concentration of the other. If we know hydronium, we can take Kw over the hydronium concentration and calculate hydroxide. If we know hydroxide, we take Kw over the hydroxide concentration and calculate hydronium. Since Kw is a constant, and it's equal to these two concentrations multiplied together, if one of these concentrations goes up, the other has to go down in order to keep Kw constant. And vice versa, if the first one goes down, then the other one has to go up in order to keep Kw constant. This may be a little bit clearer if we look at a bar chart illustrating the concentrations of these different ions. Again, we start by looking at pure water, where we have exactly equal concentrations of both, 1 times 10 to the minus 7th moles per liter, molarity. When we add an acid to a water solution, this is going to disturb the balance between these two ions. Adding an acid is going to increase the concentration of hydronium, but that's going to decrease the concentration of hydroxide so that the product of the two, Kw, stays constant. This means that in any acid solution, the concentration of hydronium will be greater than 1 times 10 to the minus 7th, and the concentration of hydroxide will be less than 1 times 10 to the minus 7th. If I add a base to a solution of pure water, then I'm going to increase the concentration of hydroxide. As a result, the hydronium concentration will have to decrease to maintain a constant Kw. In this case, we have a hydronium concentration less than 1 times 10 to the minus 7th, and a hydroxide concentration greater than 1 times 10 to the minus 7th. Anytime the hydroxide concentration is greater than hydronium, the solution is basic. There's a couple of things to keep in mind here when looking at the concentrations of these ions in a water solution. The first thing to keep in mind is that if one concentration goes above 10 to the minus 7, the other has to go below 10 to the minus 7. Both concentrations can't be above 10 to the minus 7th at the same time, and both of them can't be below 10 to the minus 7th at the same time. This is because they need to be multiplied together to equal the value of Kw, which is 1 times 10 to the minus 14. Down here in this chart, you can see various solutions that have been described in terms of their ion content. So if you take the number in the hydronium column and you multiply it by the number in the hydroxide column, you're always going to get 1 times 10 to the minus 14. It's also useful to note that anytime you have a hydronium concentration greater than 10 to the minus 7th, you have an acidic solution, and anytime it's less than 10 to the minus 7th, you have a basic solution. For the hydroxide ion, that's reversed. If it's less than 10 to the minus 7th hydroxide ion, that's acidic, and if it's more than 10 to the minus 7th hydroxide ion, then that's basic. It's also useful to see that every solution, whether it's neutral, acidic, or basic, has both hydronium and hydroxide in it. Many students fall into the trap of seeing a solution described in terms of its hydroxide content and therefore assuming that it's basic, or seeing that it has a hydronium concentration and therefore assuming that it's acidic. But every solution has both ions. What you really need to look at is the balance between the two and which of them is greater than 10 to the minus 7th and which of them is less. Let's do an example where we calculate the hydronium ion concentration from a given concentration of hydroxide ions. They're telling us that the hydroxide ion concentration, OH-, is 5.0 times 10 to the minus 8th molar. Now, before we do this calculation, sometimes it's useful to try and predict what kind of solution we're dealing with so that we can see that our answer makes sense. In this case, we need to say whether the hydroxide ion concentration that's given to us is greater or less than 1 times 10 to the minus 7th molar. That's the concentration that the hydroxide would have if this were a neutral solution. From understanding scientific notation, it should be clear that 10 to the minus 8th is going to be less than 10 to the minus 7th. Therefore, this solution has less hydroxide than a neutral solution, which makes it acidic. As a result, the hydronium concentration that we calculate should be greater than 1 times 10 to the minus 7th. Now that we can expect that, we should do our calculation. The way to calculate this is using the expression for Kw. Kw equals the hydronium ion concentration, H3O+, multiplied by the hydroxide ion concentration, OH-. Of course, we're solving for the hydronium concentration since that's what the question asks for, so we can rearrange this and say that the hydronium ion concentration, H3O+, is equal to Kw divided by the hydroxide concentration. After that, we just need to put our numbers in. Hydronium concentration equals Kw, which is always 1 times 10 to the minus 14. That's a number that you should remember. Divided by the hydroxide concentration given in the problem, which is 5 times 10 to the minus 8th. Remember that, like with equilibrium problems, we're not really going to worry too much about the units here. If we're calculating the concentration of an ion, the unit is going to be molar at the end. The units for K or Ka or Kw are all going to be unitless. So hopefully you're able to put a number or an expression like this into your calculator and get the right answer. In this case, the right answer is 2.0 times 10 to the minus 7th molar, which is indeed greater than 1 times 10 to the minus 7th molar. If you're having trouble getting it into your calculator, it might help you to do it out by hand by separating the coefficients from the powers of 10. Here you can see that the coefficient is going to be 1 divided by 5, which is 1/5 or 0.2. And the power of 10 is going to be 10 to the minus 14 minus 8. This is going to be 0.2 times 10 to the minus 6, which is actually equal to 2 times 10 to the minus 7, the way we calculated here. Let's do another example where this time we're given the concentration of hydronium, 2 times 10 to the minus 3rd, and we're asked to find the concentration of hydroxide. Again, it's useful to predict whether this solution is acidic or basic, and therefore what our answer should be, or what range our answer should fall into. So if hydronium, H3O+, is equal to 2.0 times 10 to the minus 3rd molar, it should be clear that this is greater than 1 times 10 to the minus 7th molar. In other words, this solution has more hydronium than a neutral solution would. This makes it, again, acidic. So when we calculate our concentration of hydroxide, OH-, this should be less than 1 times 10 to the minus 7th, as it would be in an acidic solution. So again, we can use the expression for Kw to calculate these concentrations. This time we're solving for OH, so we would divide both sides by H3O+. That would cancel out there, and we would get that the hydroxide concentration, OH-, equals Kw, which is 1 times 10 to the minus 14. Again, you should memorize that. Divided by the hydronium concentration, which is given to us as 2.0 times 10 to the minus 3rd. Again, you can put this into your calculator, or you can split up the coefficients in the powers of 10. The coefficient is going to be 1 divided by 2, which is 1/2 or 0.5. The powers of 10 are going to be 10 to the minus 14 minus 3, or minus 14 plus 3, which is really 10 to the minus 11. So 0.5 times 10 to the minus 11. Unfortunately, that's not quite proper scientific notation. So we have to take this as 5.0 times 10 to the minus 12th. And again, this is a molar unit. This is less than 10 to the minus 7th, and so this confirms that this is an acidic solution with a very low concentration of hydroxide.